A star dims in irregular, massive intervals, no natural explanation fits. That's not the setup to a sci-fi novel. It's the real observation that launched one of the most controversial and captivating astronomical mysteries in modern history. At the heart of this enigma lies a distant star, sitting quietly over 1400 light-years away from Earth in the constellation Cygnus. But this star isn't just any star. It's a cosmic puzzle that has left astronomers baffled, inspired wild theories, and reignited public curiosity about intelligent life beyond our planet. Some scientists think the strange dimming patterns suggest clouds of interstellar dust. Others point to disintegrating exosmays or debris from planetary collisions. But then there's the theory that set the internet on fire and captured headlines across the globe. The idea that we might be seeing the incomplete scaffolding of an alien megastructure, a sort of Dyson Sphere partially blocking the star's light as it harvests stellar energy. What makes this mystery even more compelling is how consistent the data is in its weirdness, and how inconsistent the explanations have been. This isn't a case of faulty instruments or misread signals. The Kepler Space Telescope, one of the most precise tools we've ever sent into space, watched this star closely for years and confirmed that the dips in brightness are real. These dips are deep, irregular, and unpredictable. They don't match the clean curves of a planet passing in front of its host star. They don't match anything we've seen before. This star, officially designated KIC 8462852, but more popularly known as Tabby's star, is named after astronomer Tabitha Boyajian, who first brought attention to its bizarre behavior in 2015. Since then, it has become one of the most observed and debated stars in the sky. It's been monitored by space-based telescopes, ground-based observatories, amateur astronomers, and even the SETI Institute, which searched for potential alien signals coming from the region. In this video, we're diving deep into the data behind the mystery. We'll explore the origin of the alien megastructure hypothesis and why it refuses to go away. We'll break down the natural explanations, some of which are plausible, some of which fall apart under scrutiny. We'll look at what the latest follow-up observations have revealed, what new technologies might finally uncover, and why Tabby's star continues to haunt scientists and space enthusiasts alike. Along the way, we'll encounter theories involving shattered planets, cosmic dust, energy harvesting civilizations, and the limits of our current scientific understanding. This isn't just the story of a weird star. It's a story about the edge of human knowledge, about the questions we're still learning how to ask, and the answers that might change how we see our place in the universe. So settle in. We're about to unpack one of the most compelling and confounding stories in modern astronomy. What's really happening around Tabby's star? And could it be the first sign that we're not alone? Stay with us as we begin this cosmic investigation. The discovery of a cosmic anomaly. Tabby's star was never meant to be famous. When the Kepler Space Telescope launched in 2009, it wasn't designed to find the strangest object in the galaxy. It was built with a single mission: to search for exoplanets. By monitoring the brightness of over 150,000 stars, Kepler aimed to detect the subtle dimming that occurs when a planet passes, or transits, in front of its host star. This dimming produces what astronomers call a light curve, a simple graph showing a dip in brightness over time. For most stars, this dip is small, regular, and tells a clear story about a planet's size, orbit, and distance from its sun. But something very different happened when Kepler focused its gaze on a star catalogued as KIC 8,462,852. At first, the star didn't stand out. It's an F-type main sequence star, slightly hotter and more massive than our Sun, located roughly 1,470 light-years away in the direction of the Cygnus constellation. It appeared perfectly normal in every respect, until astronomers began analyzing its light curve. Instead of small, predictable dips, Tabby's star showed deep and irregular drops in brightness. Some of these dips reached as much as 22%, far beyond anything caused by a planet. And they weren't periodic, either. The dimming didn't follow a clean, repeating pattern. It was chaotic, long-lasting, and highly unpredictable. Kepler captured the first significant dip in 2011, followed by others in 2013 and 2015, but the timing and depth varied dramatically. This kind of behavior didn't fit any known stellar phenomena. That's when Tabitha Boyajian, a postdoctoral researcher at the time, entered the scene. Working with a team of citizen scientists from the Planet Hunters project, a group dedicated to reviewing Kepler data in search of unusual light curves, she noticed that KIC 8462852 was behaving in a way no other star had before. Her analysis, published in 2015, officially brought Tabby's star to the attention of the global astronomical community. Boyajian's paper laid out the light curve in detail and explored a variety of natural explanations, from swarms of exosmays to planetary debris. But none of them could fully account for the magnitude or irregularity of the dimming events. In fact, the more scientists looked, the more baffling the situation became. The star's brightness dipped by up to 22% at times, far too much to be explained by a planet, even a gas giant like Jupiter. A planet would block only about 1% of a star's light, and the pattern would repeat predictably with each orbit. Tabby's star didn't follow those rules. The initial reactions from the astronomy community were cautious. Some suspected instrumental error, but the Kepler hardware showed no malfunctions. Others wondered if dust in the solar system or between stars could be to blame. However, the wavelength data didn't support that idea, especially since the star's dimming wasn't accompanied by the expected rise in infrared light that would suggest the presence of warm dust. Within months of Boyajian's publication, the star earned the nickname, the most mysterious star in the galaxy. Media outlets picked up the story, and speculation began to swirl. That's when the now infamous alien megastructure theory entered the conversation. Penned by a paper from Jason Wright at Penn State University, the hypothesis suggested that perhaps the irregular dimming was caused by large artificial structures orbiting the star, structures built by an advanced extraterrestrial civilization to capture its energy. While most scientists regarded this as an extreme and unlikely scenario, it had one distinct advantage: it wasn't ruled out by the data. And in the absence of a convincing natural explanation, even the wildest theories found room to breathe. The alien hypothesis wasn't proposed as fact, but it served as a placeholder, a provocative way of saying that we truly didn't know what was going on. From the moment of its discovery, Tabby's star represented something more than just an astronomical anomaly. It became a symbol of the unknown. A reminder that even in the data-rich world of modern science, the universe still has secrets to keep. The story of how this ordinary star turned into an extraordinary mystery is grounded in meticulous observation, rigorous analysis, and a willingness to confront the unexplained. This section of our journey sets the stage for what follows. Now that we understand how Tabby's star was discovered, and why its behavior so deeply defies expectation, it's time to dig into the light itself. In the next section, we'll examine what the light curve reveals, why it challenged every theory from the start, and how a flickering star has forced scientists to rethink what's possible in the cosmos. The light curve that defied logic. Light curves are the language of exoplanet discovery. For a star, its brightness over time is a steady, reliable signal, unless something is getting in the way. When a planet passes in front of a star, the dip in brightness is small, consistent, and periodic. It follows a clean pattern, creating predictable notches in the light curve that astronomers can use to determine the planet's size and orbit. This method is simple, elegant, and remarkably effective. It's how the Kepler Space Telescope confirmed thousands of new worlds across the galaxy. But then came Tabby's star, and everything changed. What Kepler recorded from Tabby's star wasn't just unexpected, it was utterly bizarre. Instead of the shallow, repeatable dips caused by orbiting planets, the star's light dimmed in a way that resembled flickering candlelight under a turbulent wind. In some events, the brightness dropped by as much as 15%. In others, it plummeted over 20%. To put that into perspective, a planet like Jupiter would only cause about a 1% dip if it passed in front of a Sun-like star. And not only were the dips extreme, they were erratic, coming without warning, following no discernible rhythm, and varying wildly in both depth and duration. The first major dip occurred in 2011, where the light dropped sharply before returning to normal. That event caught astronomers' attention, but it wasn't until 2 years later, in 2013, that another series of deep dimming events was recorded. In 2015, the star dipped again, this time with greater irregularity. By the time 2017 rolled around, ground-based telescopes had joined in monitoring the star, capturing new dimming events that confirmed the pattern was ongoing and very real. These were not isolated incidents or flukes in the data. The star was misbehaving in a sustained, unpredictable way. Statistically, the dips are staggering. The deepest ones block over 1/5 of the star's total output. Some last just a few days. Others stretch over weeks. There is no symmetry, no stable interval between events, no hint of a planet-sized object orbiting on a steady schedule. In some stretches, multiple dips occur close together. In others, the star shines steadily for months, then suddenly drops without warning. It's as if something massive, perhaps even clumpy or fragmented, is drifting across the star's face, yet no one can say exactly what that something is. When astronomers plot the light curve of Tabby's star, the result looks chaotic compared to normal planetary transits. The dips are jagged and irregular, lacking the U-shaped valleys typical of a planet passing cleanly in front of its star. Instead, the light curve features sharp edges, asymmetrical slopes, and inconsistent recovery times. Some dips fall rapidly and recover slowly, while others fade in and out in unusual patterns. If these were planetary transits, they would be among the strangest ever recorded, and likely impossible given the physics of orbital motion. Comparing Tabby's star to other known variables only deepens the mystery. Variable stars often change brightness over time due to pulsations, flares, or star spots, but these changes are generally periodic and tied to the star's internal structure. In contrast, Tabby's star appears perfectly stable in every respect. Its temperature, size, and spectrum remain consistent outside the dips. It's not spinning unusually fast. It's not part of a binary system. It doesn't exhibit strong magnetic activity. Spectroscopically, it's quiet. And yet, something is clearly disrupting the light we receive from it. Other stars have shown odd behavior, but nothing on the same scale. One example often mentioned is RZ Piscium, a young star that also experiences irregular dimming events. However, it's surrounded by a dusty debris disk, and its variability is linked to its youth and chaotic environment. Tabby's star, by contrast, is mature and stable. It doesn't appear to be surrounded by a dense debris disk, nor does it emit excess infrared radiation that would suggest large quantities of warm dust. The lack of infrared is one of the key reasons astronomers have struggled to pin down a natural explanation. Then there's the broader population of Kepler stars. Out of more than 150,000 stars observed during the mission, only Tabby's star displayed such extreme and irregular dimming. Statistically, it's an outlier by every measure. And that rarity is important. If this were a common phenomenon, astronomers would expect to find similar light curves elsewhere in the Kepler data. But the anomaly appears to be unique, at least so far, making the need for an explanation even more urgent. The light curve of Tabby's star is, in many ways, the heart of the mystery. It is the empirical fingerprint of something happening on a massive scale, and its details defy simple classification. While the Kepler data offered precision never before seen in stellar observation, it also gave scientists a puzzle without a matching box top. The dips are there. They're real. And they're not like anything else in the known stellar catalogue. This is where the search for answers begins. If planets, star spots, and dust clouds can't explain what we're seeing, what can? In the next section, we'll dig into the leading natural explanations, those grounded in conventional astrophysics, and examine why none of them, not even in combination, seem to satisfy the data. The mystery of Tabby's star is far from over, and the deeper we look, the more it challenges everything we think we know about the universe. Natural theories, trying to explain the unexplainable, when faced with an astronomical anomaly as bizarre as Tabby's star. The scientific method demands that we first rule out all possible natural causes before leaping to extraordinary conclusions. The first and most conservative explanations focused on the possibility of cosmic dust. Dust is everywhere in the galaxy, between stars, around stars, drifting through solar systems, and it has a well-documented ability to obscure light. If a large, uneven cloud of dust were orbiting Tabby's star or moving between it and Earth, it could theoretically cause the kind of dimming that Kepler recorded. However, this idea comes with significant challenges. For one, the dips in brightness from Tabby's star are not only deep, but also highly irregular. A dust cloud capable of blocking up to 22% of a star's light would have to be extremely dense and unusually cold. Normally, dust warmed by a star's radiation would glow in the infrared spectrum. This is precisely the kind of signature that instruments like the Spitzer Space Telescope and the Wide Field Infrared Survey Explorer, or WISE, are designed to detect. But when those telescopes observed Tabby's star, they found no such infrared excess. The star appeared as ordinary as any other, without the telltale signs of a dusty environment. That absence is critical. It means that if dust is the culprit, it must be composed of very fine particles that absorb light unevenly across different wavelengths and remain strangely cold for their proximity to the star. Another early contender was the exoplanet hypothesis. This theory proposed that a family of long-period comets, possibly disrupted by a passing star or gravitational interactions, had broken apart and were now shedding debris across the line of sight to Tabby's star. These comet fragments, surrounded by gas and dust, might account for some of the erratic dimming. Initially, this idea was seen as one of the most plausible. It explained the irregular timing, the varying depth of the dips, and the possibility of fragmented or clumpy material moving in loose formation. But the exoplanet theory also runs into problems. For this to be happening over the timescale observed, the system would need to be producing an enormous number of comets, continuously replenishing the obscuring material for years. Yet there is no evidence of such high activity around the star. And again, there is a lack of infrared emission that should be expected from this much icy material sublimating in the heat of the star. Without the thermal signature to back up the hypothesis, the comet idea becomes increasingly hard to justify. Some astronomers turned their attention to interstellar material. Perhaps the dips in brightness were being caused not by anything orbiting Tabby's star, but by clouds of gas or dust drifting between the star and Earth. Interstellar medium, composed of diffuse hydrogen and dust particles, can scatter and absorb starlight in subtle ways. It's not unthinkable that a poorly understood patch of space debris could be responsible. But this explanation comes with its own set of flaws. Interstellar dust tends to dim light uniformly, or at least predictably, across different wavelengths. The behavior of Tabby's star's dips, especially their asymmetrical, non-periodic nature, doesn't align with the characteristics of interstellar absorption. The timing of the dips is too sharp, and their profile too dynamic, to fit the slow, uniform filtering of interstellar matter. Perhaps the most violent idea proposed was that of planetary debris from a shattered world. Imagine a massive collision between two large bodies, something akin to the impact that formed Earth's moon, but on an even greater scale. The aftermath would be a dense, chaotic ring of rock and dust, possibly obscuring light as it orbits the star. This theory gained traction because such collisions are a natural part of solar system evolution. However, the absence of warm dust again undercuts the idea. A recent planetary collision would produce vast amounts of hot material, glowing in the infrared, especially if it was ongoing or recent enough to cause multiple dimming events across several years. The notion of asteroid swarms or colliding minor planets falls into a similar category. A swarm of objects moving in a loose group might block light in irregular bursts. But to match the depth and unpredictability of the dimming observed at Tabby's star, the swarm would need to be enormous in both mass and spatial extent. This scenario also fails to explain why we don't see more stars behaving in this way. If asteroid swarms of this kind were common, Kepler should have observed more anomalies like this. Instead, Tabby's star stands alone. The most damaging evidence against all of these natural theories comes from infrared studies. Both the Spitzer Space Telescope and WISE were trained on Tabby's star in the wake of the Kepler findings, specifically to search for warm dust, gas, or other obscuring matter. The results were clear and consistent. No significant infrared excess was detected. This puts a hard limit on how much dust or debris can be present in the system, severely constraining all theories based on physical obstructions. If something is blocking the light, it's doing so without emitting heat, or it's positioned in such a way that it avoids detection entirely. That is a high bar to clear for any natural explanation. To add perspective, let's consider a comparison case. RZ Piscium, a young and active star in the Pisces constellation, also displays erratic dimming behavior. It's surrounded by a dense debris disk, likely the remnants of recent planetary destruction. The infrared signature from RZ Piscium is obvious and intense, which aligns perfectly with what scientists expect from a star surrounded by dusty chaos. Tabby's star, by contrast, exhibits none of these signs. It is mature, quiet, and spectrally stable. Whatever is causing the dimming is not throwing off excess heat or behaving in a way that mirrors known examples. Each of these natural explanations, dust clouds, exosmaze, interstellar matter, planetary debris, and asteroid swarms, carries theoretical weight. But each falls short when tested against the full suite of observational data. In science, the simplest explanation is usually the right one. But in the case of Tabby's star, simplicity offers no refuge. The light is dimming. The patterns are strange. And the mechanisms we rely on to explain the cosmos just aren't enough. As natural theories falter, curiosity grows. What if the answer isn't dust, or debris, or destruction, but something entirely different, something artificial? In the next chapter of this story, we'll explore the most provocative idea ever proposed to explain the mystery of Tabby's star, the possibility that we are witnessing the construction, or decay, of an alien megastructure. It's bold, controversial, and maybe even a little terrifying. But before we dismiss it, we need to understand why scientists were even willing to entertain it in the first place. The alien megastructure hypothesis, when natural explanations fail to fully account for an astronomical mystery, the door, however reluctantly, opens to more unconventional ideas. In the case of Tabby's star, that door led to one of the most provocative hypotheses in modern astrophysics: the possibility that we might be witnessing the presence of an alien megastructure. Though the scientific community approaches such claims with caution, the idea didn't come from a conspiracy blog or a late-night sci-fi forum. It came from a long-standing theoretical concept grounded in real astrophysical reasoning, first proposed by one of the 20th century's most respected physicists. In 1960, theoretical physicist Freeman Dyson introduced a concept that would later bear his name. He proposed that a sufficiently advanced civilization would inevitably seek to maximize its energy consumption by capturing as much of its star's output as possible. One way to achieve this, Dyson argued, would be to construct a vast shell or swarm of structures around the star, capable of intercepting and utilizing its radiant energy. This hypothetical construction became known as a Dyson Sphere, not necessarily a solid shell, but perhaps a swarm of orbiting panels, habitats, or collectors engineered by a civilization far more advanced than our own. The logic was simple yet profound. As civilizations evolve, their energy needs grow. A planetary society like ours, classified as a Type 1 civilization on the Kardashev scale, harnesses the energy available on its home planet. A Type 2 civilization would be able to capture the full energy output of its host star. A Dyson Sphere would be a natural outcome of such a civilization's development, a vast, artificial structure designed not for concealment, but for efficiency. Fast forward to 2015. When Tabitha Boyajian's team published the unusual light curve data of KIC 8,462,852, the astronomical community began scrambling for answers. The light dips were unlike any seen before, deep, erratic, and lacking the infrared signature that might suggest natural dust. Around that time, Jason Wright, an astronomer at Penn State University, suggested that if all natural explanations failed, one possible cause could be a megastructure built by an advanced civilization. While not a formal claim of discovery, the idea was a reminder that Kepler's mission had opened a new chapter in our ability to detect anomalies that might not fit into traditional frameworks. The reason the alien megastructure hypothesis gained traction wasn't just because of the lack of natural explanations. It was because the pattern of dimming from Tabby's star, while chaotic, could be loosely interpreted as consistent with large, uneven structures orbiting the star in a disorganized or partial formation. Unlike the clean silhouette of a planet, an incomplete swarm of artificial satellites or energy collectors could cause irregular, asymmetrical dips in brightness. And if these structures were not thermally active, constructed from highly reflective, low-emission materials, they might evade detection in the infrared spectrum. Once the suggestion was made, the story exploded beyond the scientific journals. Media headlines seized on the phrase, alien megastructure, and within days, Tabby's star became an internet sensation. News outlets around the world ran stories speculating about intelligent life, ancient technology, and civilization-spanning engineering. The public imagination was ignited, not necessarily because people believed it was aliens, but because it was one of the few times the scientific community openly entertained the possibility, however cautiously. The involvement of the SETI Institute added even more intrigue. SETI, the search for extraterrestrial intelligence, had long been monitoring the cosmos for signs of intelligent life, typically through the detection of radio signals or optical beacons. Upon learning of Tabby's star's behavior, SETI directed its powerful Allen telescope array to the region of space containing KIC 8,462,852. The goal was to scan for any artificial radio emissions that might suggest communication or technological activity. Over several observation campaigns, SETI listened intently. The Allen telescope array scanned multiple frequencies in hopes of detecting narrow bandwidth signals, something no known natural source produces, but which could be used by intelligent civilizations. The result? Nothing definitive. No clear signal. No radio whisper from the stars. Silence. This result was not unexpected. Even if an advanced civilization were harvesting stellar energy near Tabby's star, it doesn't follow that they would be broadcasting signals in our direction, or in a way we could interpret. It's also possible that any signals being emitted fall outside the narrow bands we currently monitor, or that they're encoded in ways beyond our comprehension. The absence of a signal isn't disproof of intelligent life. It simply means that, if such life exists there, it's not currently communicating in a way we can detect. As exciting as the alien megastructure theory is, it carries inherent limitations. The dimming pattern does not exhibit a clear technological signature. There's no evidence of repeating geometric structures, no synchronized timing, no mathematically organized light curve that might suggest engineered behavior. The data remains messy and irregular. If it is a megastructure, it's a very strange one, perhaps unfinished, damaged, or decaying. But that pushes the theory further into the realm of speculation. Still, what keeps this idea alive isn't the strength of the evidence, but the weakness of all alternatives. When a mystery refuses to resolve itself with known natural processes, the possibility, however remote, that it's the product of intelligence must at least be considered. In the vastness of the universe, with billions of stars and perhaps even more planets, the odds of encountering something beyond our understanding aren't zero. Tabby's star stands as a kind of cosmic Rorschach test. Some see dust. Some see destruction. Some see aliens. And some see the limits of our current scientific reach. The alien megastructure theory may not be the answer, but it was never meant to be the default explanation. It was proposed as a last resort, a sign that our models have gaps, and our tools, however sophisticated, are still learning how to interpret the universe's more cryptic signals. In the next part of this journey, we'll step away from speculation and return to the data. We'll examine the ongoing investigations into Tabby's star, how scientists continue to observe, model, and debate the mystery. New observations have added layers of complexity to the puzzle. And though the alien megastructure theory continues to make headlines, it is the slow, careful work of follow-up science that may eventually bring clarity to this shadowy cosmic drama. The science continues, ongoing observations and debate. After the initial discovery of Tabby's star's irregular dimming behavior and the explosive attention it received, the scientific community quickly mobilized to gather more data. If there's one thing astronomers rely on to navigate cosmic uncertainty, it's the power of patient observation. Kepler's original data had opened the door to one of the strangest light curves ever recorded. Now, it was up to ground-based observatories and global networks of astronomers to continue watching and searching for patterns that might offer clarity. What followed was one of the most collaborative, persistent, and yet still inconclusive follow-up efforts in recent astrophysical history. The Las Cumbres Observatory Global Telescope Network became one of the major players in monitoring Tabby's star after Kepler. This unique network of telescopes spans both hemispheres, allowing for nearly continuous observation across different time zones and geographic locations. In collaboration with professional astronomers, citizen scientists, and institutions like Louisiana State University, Las Cumbres provided high-cadence photometric data from 2016 onward. These observations became vital in detecting any new dimming events that might shed light, ironically, on the shadowy activity surrounding the star. In 2017, the collaborative efforts paid off. Tabby's star dimmed again, several times throughout the year, and this time the scientific world was ready. Thanks to ground-based monitoring, these dips were caught in real time, confirming that the phenomenon wasn't a one-off anomaly captured by Kepler. This wasn't a ghost in the data or an instrument malfunction. It was real, persistent, and actively continuing. What made this even more exciting was that astronomers now had the opportunity to observe the dips across multiple wavelengths, capturing data in the ultraviolet, visible, and infrared bands simultaneously. That same year saw one of the most fascinating moments in modern astronomy. Not from a massive observatory, but from the grassroots energy of thousands of observers contributing to the effort. Organizations like the American Association of Variable Star Observers, or AVSO, mobilized amateur astronomers around the world to keep watch on Tabby's star. This crowdsourced campaign resulted in nearly continuous coverage of the star's brightness levels, with hundreds of data points submitted by individuals using small telescopes from their backyards. In the age of digital technology and networked collaboration, science had truly become a global, shared effort. As the data continued to flow in, astronomers began to publish new peer-reviewed analyses, debating the implications of the multi-wavelength observations. One of the key questions was whether the dips occurred equally across all parts of the light spectrum. If the dimming were caused by solid objects, such as alien structures or opaque debris, the drop in brightness would be the same at all wavelengths. But if dust or semi-transparent material was to blame, shorter wavelengths like blue light would be absorbed more than longer red wavelengths. Observations from 2017 showed exactly that. The dips were stronger in blue light, consistent with fine dust particles scattering the light in a wavelength-dependent fashion. This finding nudged the scientific consensus back toward dust-based explanations. But it didn't solve the mystery entirely. While the color-dependent dimming supported the presence of dust, it didn't explain where the dust was coming from, why it appeared so irregularly, or why it remained so cold and elusive in infrared surveys. If dust were the sole explanation, it would have to be of a very specific composition, extremely fine, and unevenly distributed in ways never observed before. The result? One explanation gained traction, but even that couldn't close the case. The European Space Agency's Gaia mission also added a new layer of information in its data releases. Gaia, tasked with mapping over 1 billion stars in the Milky Way, provided unprecedented detail about the motion, distance, and age of stars, including Tabby's star. Gaia's data confirmed that KIC 8,462,852 is a mature, main-sequence F-type star, not young or unstable. This is a crucial piece of the puzzle. If the star were young, some of the strange behavior might be attributed to leftover planetary debris or a chaotic formation environment. But a mature star is expected to be more stable, with fewer surrounding materials to cause such dramatic dimming. With all this information, the repeated dimming events, the absence of infrared excess, the color-dependent light curves, and the stellar profile from Gaia, astronomers were left with a paradox. The more data they collected, the more complex and contradictory the picture became. Each new observation added a detail that ruled out one theory but failed to support another. The dust appeared to fit, but only if it behaved in ways dust isn't supposed to. The megastructure idea couldn't be completely dismissed, but it lacked the repeatable, geometric precision expected of an artificial design. And no other stars observed by Kepler, or any other instrument, showed exactly the same kind of behavior. The scientific debate continues, often centering around hybrid models. Perhaps the cause is a combination of dust and disintegrating bodies, or a disrupted planetary system with highly variable debris. Some theorists have suggested large ring planets with dynamic orbital material, or even fragments of a planet being torn apart by the star's gravity over time. Others entertain the possibility of exotic astrophysical phenomena we simply haven't encountered before. Whatever the true explanation, it's clear that no single theory currently satisfies all of the observational constraints. This resistance to easy answers is what makes Tabby's star so enduringly fascinating. In an age where data collection is more powerful than ever, the idea that a star could still behave in such a mystifying way reminds us of the limits of our understanding. It is not just a challenge to current models of stellar behavior, it's a challenge to our assumptions about how the universe operates. This star refuses to fit inside the neat boxes that science has built, and in doing so, it pushes the boundaries of what we believe is possible. As the research continues, so does the conversation. Tabby's star has become more than just an object of study, it has become a symbol of the scientific process itself. Observation, collaboration, skepticism, and curiosity are all on display in the way this mystery unfolds. And while the truth may eventually emerge from the data, the path to that truth is proving to be every bit as compelling as the answer itself. In the next chapter, we'll turn to the human side of the mystery, how public fascination, speculation, and controversy have played just as important a role in shaping the story of Tabby's star as the telescopes and data behind it. A star that captured the public imagination. The moment Tabby's star was introduced to the public consciousness, it transcended the bounds of academic journals and telescope data. What began as a dry light curve anomaly buried in the Kepler mission's ocean of data quickly evolved into a cultural sensation. Science news outlets ran with it first, using headlines that ranged from the cautious to the outrageous. But it wasn't long before mainstream media joined in, spurred by the tantalizing whisper of a phrase rarely invoked seriously by scientists: alien megastructure. Overnight, Tabby's star became the strangest, most captivating object in the galaxy that nobody had ever heard of before. For many, the appeal was immediate and powerful. Here was a star doing something no other star had done before. It wasn't just blinking or flaring, it was behaving in a way that defied every natural explanation, or at least every well-established one. The public doesn't often get to see scientists genuinely perplexed, and even less frequently do they witness a situation where leading researchers openly admit, with complete honesty, that they have no clear answer. That mystery, and the humility it revealed in the scientific process, resonated widely. In a world increasingly skeptical of experts and institutions, Tabby's star offered a moment of shared curiosity and wonder. But the story also highlighted a stark divide. While the public leaned into the idea of alien civilizations and megastructures, the scientific community responded with measured skepticism. Researchers were careful not to sensationalize the alien hypothesis, constantly reiterating that it was a last resort idea, to be entertained only after exhausting every natural explanation. And yet, despite their caution, they couldn't completely rule it out. That ambiguity left just enough space for imagination to flourish, and in that space, the internet did what it does best. As interest soared, so too did the desire to keep studying the star. But telescope time is limited, and funding for observational campaigns is often tied to more conventional projects. In an unprecedented move, Tabitha Boyajian and her team launched a crowdfunding campaign to support further research. The response was extraordinary. In a matter of weeks, thousands of donors raised more than $100,000 to fund ongoing monitoring of Tabby's star. The campaign was not only successful, it was historic. It marked one of the first times a major scientific investigation into an astrophysical anomaly had been funded directly by the public. This act of crowdfunding turned observers into participants. Supporters weren't just watching the mystery unfold, they were helping solve it. The campaign also gave rise to a network of amateur astronomers and science enthusiasts who began following the star's activity closely. Social media feeds tracked the star's brightness like a stock ticker. Forums and subreddits dissected each new observation in real time. In many ways, Tabby's star became the internet's first truly interactive cosmic mystery. The story also gave new life to the broader search for extraterrestrial intelligence. SETI, which had long operated on the margins of mainstream science, found itself at the center of attention once more. The possibility, however slim, that Kepler had stumbled upon evidence of an advanced civilization reignited interest in SETI's mission. Suddenly, the search for alien life was no longer just about listening for radio signals, it was about scanning light curves, modeling dust clouds, and interpreting the subtle behavior of stars. It became a multi-dimensional quest, one that brought together astrophysics, data science, and philosophical inquiry. For many, the mystery of Tabby's star evoked memories of another unresolved cosmic anomaly, the WOW signal. Detected in 1977 by a radio telescope at Ohio State University, the WOW signal was a brief but powerful burst of radio energy that fit the expected profile of a signal from an intelligent source. Despite extensive follow-up searches, it was never detected again. Like Tabby's star, the WOW signal sits at the edge of credibility and wonder, tantalizing but inconclusive. Both serve as reminders of how little we truly know, and how much we still have to discover. In both cases, the public response was driven by a deep, almost primal question: are we alone? Tabby's star didn't answer that question, but it reignited it in a way few other discoveries have. It reminded people that the universe is vast and strange, and that within that strangeness lies the potential for something extraordinary. Whether it's an alien megastructure, a weird dust cloud, or something else entirely, Tabby's star captured the world's attention by breaking the rules and refusing to explain itself. In doing so, it bridged the gap between scientific inquiry and public imagination. It showed that even in the age of high-resolution imaging and AI-driven analysis, there is still room for awe. It proved that a single star, blinking strangely in the darkness, could unite scientists, skeptics, dreamers, and everyday observers in a shared sense of wonder. As the public followed every update, every new dip in brightness, and every shift in scientific consensus, the star became more than an object, it became a mirror. A mirror that reflected our hopes, our doubts, and our endless curiosity about what else might be out there. In the next section, we'll explore just how deep those implications go. Because Tabby's star isn't just about what we know. It's about what we dare to imagine in the face of the unknown. The deeper implications of a flickering star are beyond the numbers, models, and debates. Tabby's star invites a larger reflection, one not just about astrophysics but about our relationship to the unknown. When people first heard about the bizarre light dips from a star over 1,000 light-years away, many latched onto one idea almost immediately. Could it be aliens? That question wasn't just idle curiosity or pop culture conditioning. It came from somewhere deeper, rooted in our own psychological and philosophical desire for connection, for meaning, and for cosmic validation. We want it to be aliens, not because we are desperate for an invasion or a galactic revelation, but because we are desperate not to be alone. This longing speaks to our nature as meaning-seeking creatures. The universe is vast, so vast, in fact, that our own existence feels like an anomaly. When we find something we can't explain, especially something as peculiar and persistent as Tabby's star, we instinctively project our own intelligence onto it. This act of projection isn't new. It's a continuation of our long history of anthropocentrism, where we interpret the unfamiliar through a human lens. We imagine life elsewhere acting like us, building things we might build, sending signals we might send, and leaving signatures that echo our own developmental trajectory. But the cosmos has no obligation to behave in ways we understand. The very idea of a Dyson sphere is, at its core, a reflection of our own logic. It stems from the assumption that advanced civilizations will scale up their energy consumption just as we have. Yet this assumption reveals more about our values than it does about potential extraterrestrial life. Perhaps intelligent beings out there don't follow the same thermodynamic priorities. Perhaps their civilizations don't rely on stellar output at all. The moment we suggest that aliens might be responsible for the light dips, we also reveal how deeply tied our theories are to our own technological biases. This tension, between scientific restraint and public imagination, has defined the Tabbys star conversation from the beginning. On one hand, scientists have a responsibility to work within the framework of known physics, to exhaust all plausible natural explanations before leaping to extraordinary ones. That caution is necessary. It prevents science from slipping into fantasy. But it also creates a contrast with the public, who are often more open to extraordinary possibilities, unburdened by the methodological rigor that defines academic discourse. The result is a strange kind of dance. Scientists say, probably not aliens, and the public hears, possibly aliens. The gap between what is said and what is heard is filled with hope, skepticism, and everything in between. At the heart of it all is a reminder of just how little we truly understand. Tabby's star remains unexplained not because we haven't tried hard enough, but because the universe is still far more complex than our models can capture. It's a humbling reminder that even with our most advanced tools, there are still signals in the sky that resist classification. We often imagine ourselves at the pinnacle of understanding, yet we continue to encounter phenomena that force us to re-evaluate that position. Tabby's star is not a crack in science, it's a window into its limits. This mystery also echoes the most enduring question in the search for extraterrestrial intelligence. If the universe is teeming with life, where is everyone? Known as the Fermi paradox, this contradiction between the high probability of intelligent life and the complete lack of contact has puzzled thinkers for decades. Tabby's star doesn't solve this paradox, but it adds a wrinkle. It suggests that the signatures of alien life, if they exist, might not come in the form of radio waves or interstellar messages. They might appear as anomalies, as puzzles, as light curves that don't quite make sense. Is Tabby's star a signpost pointing to life beyond Earth? Or is it another cosmic dead end, a quirk of physics yet to be fully unraveled? Either answer reshapes our understanding. If it's aliens, we are not alone, and the implications of that are staggering. If it's not, then the mystery is even more profound, because it means the universe can still surprise us with phenomena we've never imagined. In either case, we are reminded that the cosmos is not only stranger than we suppose, but perhaps stranger than we can suppose. To explore this further, we return to the Drake equation, a formula developed by astronomer Frank Drake in 1961 to estimate the number of intelligent civilizations in the galaxy capable of communication. The equation includes variables like the rate of star formation, the number of habitable planets, the likelihood of life emerging, the probability of intelligence developing, and the lifespan of technological civilizations. While each term remains uncertain, the Drake equation remains a useful tool for organizing our ignorance. Tabby's star challenges us to revisit some of these terms. If the anomaly were evidence of intelligent activity, it would dramatically increase our estimate for the number of detectable civilizations. But even if it's not, it still forces us to think more broadly about the kinds of signatures we should be looking for. Perhaps we have been too focused on radio signals, ignoring other indicators of intelligence. Maybe light anomalies, unusual spectral fingerprints, or unexplained motion patterns are equally valid signs of advanced activity. It also raises the possibility that civilizations may not want to communicate, or that their technologies are so advanced they appear indistinguishable from natural processes. Arthur C. Clarke once said that any sufficiently advanced technology is indistinguishable from magic. Tabby's star reminds us that some phenomena might be indistinguishable from silence, or from error, or from simple yet undiscovered physics. In the end, the flickering light of Tabby's star does more than spark theories. It inspires reflection on science, on our place in the cosmos, on the limits of reason and the reach of imagination. It brings us face to face with the unknown, and in doing so, it pulls us out of our routines and into a larger cosmic story. Whether that story includes others like us is still a question. But the search, fueled by data, driven by curiosity, and tempered by humility, continues. And that, perhaps, is the most meaningful implication of all. Evolving theories and emerging technology. As of 2025, the mystery of Tabby's star remains unsolved, but it has continued to evolve in the hands of astronomers armed with new tools, more data, and refined hypotheses. Though no single theory has managed to fully account for the bizarre dimming behavior, the latest wave of research is pushing the boundaries of what we know, and how we analyze the unknown. Scientists are refining earlier ideas, exploring novel interpretations, and using cutting-edge technology to inch closer to a resolution. One of the most promising recent developments involves sophisticated dust models that go far beyond the simplistic assumptions of earlier theories. Researchers are now examining scenarios where non-spherical, asymmetric dust particles, perhaps composed of exotic minerals, could cause highly irregular light scattering without producing the usual infrared emissions. These particles might be unusually efficient at blocking visible light while remaining nearly invisible at longer wavelengths. In some models, this dust is being generated not by exosphere asteroid swarms, but by processes involving ringed planetary bodies or moon systems that have become destabilized and begun shedding material. The interaction of these materials with stellar radiation could lead to complex, time-variable dimming events. Another intriguing possibility lies in magnetospheric activity. Some theorists have proposed that interactions between the star's magnetic field and nearby orbiting bodies might be generating large-scale structures of charged particles that distort the light in transient, non-periodic ways. While this idea is still speculative, it represents an important shift, away from purely physical obstructions like dust or debris and toward more complex, plasma-based interactions. If magnetospheric mechanisms are at play, it would mean the star's own behavior is partially responsible for the light anomalies, rather than passive objects drifting in front of it. Adding to this toolkit is the growing role of artificial intelligence in anomaly detection and classification. With enormous datasets from observatories like Kepler, TESS, and Gaia, astronomers are increasingly relying on machine learning algorithms to identify patterns too subtle or complex for the human eye. AI is especially useful for flagging rare events, like the initial behavior seen in Tabby's star, and comparing them across thousands or millions of other stars. Some models are now being trained specifically to search for light curves that deviate from expected planetary transits, making it easier to identify new candidates that might exhibit Tabby-like behavior. These systems are also helping refine existing theories by analyzing the statistical distribution and clustering of dips, suggesting which mechanisms might be more likely. As for instruments with the potential to offer breakthrough insights, the James Webb Space Telescope has been a focus of hope. With its powerful infrared capabilities, JWST was expected to detect even the faintest thermal emissions from dust or debris that previous observatories missed. However, Tabby's star has not yet been one of JWST's primary targets, likely due to scheduling priorities and the lack of a known dimming event during its early operational window. That said, astronomers continue to advocate for time on JWST to observe the star during future dips. The telescope's sensitivity and precision could finally confirm or rule out subtle thermal signatures that would distinguish between different dust compositions or particle sizes. Looking ahead, other missions may be better positioned to crack the mystery. NASA's upcoming Nancy Grace Roman Space Telescope, scheduled for launch later in the decade, will carry a wide-field instrument ideal for monitoring large regions of the sky with high resolution. While not designed specifically for anomaly hunting, its deep survey capabilities could uncover more stars with Tabby-like dimming, providing valuable context and helping determine whether KIC 8,462,852 is truly unique or simply the first in a class of similar phenomena. Additionally, advancements in spectroscopy and high-precision photometry from ground-based instruments are enabling more detailed studies of stellar light, potentially revealing subtle shifts in composition or motion that earlier surveys could not detect. The truth behind Tabby's star may not be hidden in a single dataset or solved by one theory. Instead, it might emerge through the accumulation of insights from multiple tools, each contributing a piece of the puzzle. As technologies evolve, so too does our ability to interpret the cosmos. And while this one star continues to defy explanation, it is also pushing science forward in ways no one anticipated. After years of observation, analysis, debate, and speculation, Tabby's star remains one of the most compelling astronomical enigmas of our time. From the moment the Kepler Space Telescope captured its inexplicably erratic dimming patterns, scientists have been chasing answers across the full spectrum of possibility. They've built and tested intricate dust models, evaluated comet swarms and planetary debris, explored exotic interactions between stellar magnetism and orbiting matter, and even allowed themselves, cautiously, to consider the prospect of alien megastructures. And yet, despite all of this effort, the core question remains unanswered. What is causing Tabby's star to flicker in such a chaotic and unprecedented way? No natural explanation has been able to account for every observation. The dust theories make sense until you remember the missing infrared signatures. the Exoplanet models fall apart under the weight of required numbers and lack of thermal emissions. Planetary collisions, asteroid swarms, interstellar matter, all offer fragments of plausibility, but none provide a full and satisfying picture. Even the alien megastructure hypothesis, though captivating and rooted in serious theoretical groundwork, doesn't neatly fit the irregularity and inconsistency of the data. We're left with a mystery that resists resolution, one that humbles our understanding and ignites our imagination all at once. And maybe that's the most important takeaway. Tabby's star challenges us to embrace the unknown not as a failure of science, but as an invitation to keep going. It asks us to stay open to discovery, to refine our tools, to question our assumptions, and to never stop looking up. Science thrives not on certainty, but on curiosity. Every mystery is a doorway to deeper understanding, even if that door opens slowly, over decades or longer. The story of this flickering star isn't just about the search for answers. It's about the process of inquiry itself, careful, collaborative, and always evolving. So as we wrap up this journey through light curves, theories, debates, and dreams of intelligent life, consider what makes this star so unforgettable. It isn't just the data. It's the way that data echoes through our imaginations, the way it invites each of us to wonder what else might be out there, hiding in plain sight. Whether you're a scientist, a stargazer, or just someone drawn to the mysteries of the cosmos, Tabby's star reminds you that the universe still holds secrets, and that the search is far from over. If you've enjoyed diving into this extraordinary cosmic puzzle, make sure to subscribe for more deep space mysteries and science-driven explorations. Every week, we take you beyond the headlines and into the strange, fascinating corners of our universe. And now we want to hear from you. What do you think is hiding around Tabby's star? Is it dust, destruction, or something beyond our wildest theories? Drop your thoughts in the comments below. The conversation doesn't end with the video, it begins with your ideas. Coming up next, a look at another unexplained signal from space that still haunts astronomers to this day. In our next video, we're diving into the wow signal and other mysterious messages from the cosmos that defy easy interpretation. Until then, stay curious, keep questioning, and remember that sometimes the biggest discoveries start with a flick.